CAD model of the design. You convert the CAD model to an STL format, which is called a stereolithography format. You slice the STL file into thin cross-sectional layers. You construct a model one layer atop the other. You clean and finish the model. That is the fifth step. Now, when it comes to the first one, with the CAD model creation, first, of course, you can build it using any computer-aided software package that you know. And then you can also use an existing CAD file, or you can create one for maybe prototyping purposes. Now, the second, which is converting the CAD model to STL format. There are several of these CAD packages that have different algorithms to represent a solid object. But because you want to be consistent, the stereolithography is a file format that has been built into most of the software, called the extension file is XTL. So you just simply export the path into the STL format. Now, what happens during the process that it's basically convert the CAD file into this STL format and represents a three-dimensional surface as an assembly of planar triangles. Now, the file will contain the coordinates of the vertices and the direction of the outward normal on each triangle. And then the files basically use these planar elements, and they cannot present curved surfaces exactly. Now, if you want the process to approximate the product, quite closely, then you will have to increase the number of triangles, but that will increase the size of the file, and then that has an impact on cost. So you can, in such a situation, when you have a very large and complicated file, it requires a lot of time or more time to pre-process and build. And so you have to balance accuracy with manageability of to produce the useful STL file. Because if you want to be very accurate, then it is going to be expensive, because it will take a longer time to build the part and then to process. So this STL file is quite universal. You can see it in several softwares. So it becomes an identical for all the rapid prototyping build techniques. Now, the third step after converting the file to an STL file is that you slicing of the STL file. Now, it is a pre-processing program that prepares the STL file to be built. Now, there are so many programs available that allow the user to adjust the size, location, orientation of the model. And the orientation of the model is very important when we are creating the STL file. So we say that first, properties of the rapid prototypes vary from one coordinate direction to another. For example, if you are building prototypes, they are usually weaker and less accurate in the vertical direction than in the XY plane. Now, because of that, it means you place the shortest dimension in the Z direction. That then makes sure that the number of layers are reduced, and then shortening the build time. Now, the pre-processing software slices the STL into a number of layers. Now, these are very thin layers, in the order of 0.01 of a millimeter to 0.7 millimeter thick, depending on the build technique. And the program may also generate some auxiliary structure to support the model during the build. Now, the supports are useful for delicate features such as overhangs, internal cavities, and thin wall sections. Now, each prototyping machine manufacturer supplies their own what we call the pre-processing proprietary software. Now, the fourth step basically is the actual construction of the part. Now, it uses one of the several techniques that are going to be described. We have rapid prototyping machines building the parts one layer at a time for the polymers, paper or powdered metal. And then most machines are fairly autonomous. That is, when you close it and you start it, you just leave it, and then by the time it's complete, you just open and take your part. Now, the last step is the final step, which is cleaning and finishing. That involves removing the prototype from the machine, detaching any support. Some of these photosensitive materials have to be cured before use. So there is an oven that the part will be sent in, and the curing process will continue. And then you have some prototypes that also may require some minor cleaning and surface treatment, which is done including some painting, sanding, and sealing, and that is to be done to improve the appearance and then durability. Now let's go into the techniques. We have at least 6 different techniques, rapid prototyping techniques, that are commercially available. Each one has its unique strength. Now these techniques include: 1, we call the stereolithography; 2 is laminated object manufacturing; 3, selective laser sintering; and then 4, we have fused deposition modeling; 5, the 3D inkjet printing; 6, solid ground curing, SGC. Now, when it comes to STL, that is the stereolithography. This is the first technique which was patented in the 1986, and that's actually started this whole rapid prototyping revolution. Now, basically the technique builds the 3-dimensional model from a liquid photosensitive polymer. Basically, you have the polymer in this layer, that's the liquid polymer here, and then you have a laser or a low power highly focused UV laser, which is coming with the geometry of the part, and then it traces out the first layer from the STL file, layer by layer, and then it solidifies the model cross section, leaving the excess liquid. Then what happens is that you have an elevator that will then lowers the part, the platform into the liquid polymer, and then the sweeper comes to sweep or recoats the surface with the liquid. And then the laser, the second laser will then shine that cross section of the drawing. Because the files have been sliced into the STL file, it's carried layer by layer construction. After that, you remove the solid part. Now, this can be best explained in this video that we're going to watch out very quickly. So I'm going to show you this video, which is roughly a 7-minute video. So let's watch this.
Moving products quickly from design to market is imperative in every industry. It means staying ahead of competition, staying up on the customer. The reduced cycle time to bring Explorer to market is a good example of that. The DCX single-stage water demonstrator is another. Rapid prototyping moves that prototype from concept to operating platform. A little over 18 months.
are made and a drawing is turned out, we can get the physical part and see if it's going to clear the structure, it's going to clear the wire models, fit up to the pins, right? If there is a problem, you can make the correction before you release the drawing, or if it works fine, then you know that you're doing the right thing, investing in a tool before you do it. When a designer has a part, like us to make a stereo designer, he gives us a three-dimensional CAD image that is either a surfaced or solid format. And the first step we do is on Unigraphics, there's a program that will re-represent the geometry of the part in little bitty triangles, facets. And the output of the program then gets sent to a regular DOS computer that will then take all of that data, arranging it into several layers. So thousands actually. These layers will then be sent to the stereolithography machine. Works by using ultraviolet light that is provided by laser to solidify it with photosensitive protocol. Wherever the beam shines on it, it causes this present solidity. The process starts out where an elevator platform is positioned right at the surface level of the residue, and the ultraviolet light shines in the shape of the cross-section of the first layer. And when the first layer is completed, the elevator drops down to let fresh resin run over top of that resin that's already been solidified. And the platform positions itself one layer thickness lower than it just was to let the second layer solidify. Then it drops down again for fresh resin, and comes back up, does a third layer, fourth layer. It's as if we were to take, say, a deck of cards, and each card cut out in the shape of a cross-section of a part, and you stack them all up, you end up with a coffee cup or parts to the F-18 or whatever it is the designer wanted. When a part is finished in the machine, it comes up out of the liquid and it's got support structure that is attached to the platform while it's being built. So we need to remove it from the platform, rinse it in a solvent to get the uncured liquid off, and then we have to do some post-cure. So we have a cover that is about like a tanning booth that puts off ultraviolet light and finishes curing the part. The part is actually deliverable in that state, but occasionally we have people that want to have a finished part where it's painted. But this is one of my favorite parts to demonstrate the work of this. It's a little fan blade, and if you gave me the CAD model to this, I could process the data and run it in the machine probably even before the day is over, have it back in your hands. You could probably the next day have this on the motor shaft, spin it up, and try to cool the equipment that you're going to use to have this thing cool, and find out the results if your designer was going to do the job. With conventional models, this will probably take a week or 2 weeks minimum. Actually, most parts that we make are not nearly that small. In fact, a lot of them are so big that we can't even make them in one piece. For example, this one, that's not at all a problem. This was too big for us to make in one piece. So we just, in this case, the lower portion of this was made in the machine, and I made this separately, and we just put the two pieces together. We've had some pieces that are over 4 feet long that we put together in sections and pull some apart. The F-18 has been our biggest customer, had several portions of the wings where, especially with the hydraulic actuators controlling the control surfaces, the designers have wanted to see if they had enough clearance to get the parts in and just to see if everything was going to work out all right. And when you just have a blueprint, the producibility engineer
Okay, so we watched the video and then we saw the whole technique of rapid prototyping. They had a machine that basically we described over here, where the laser beam was shining and producing the part. Now, I will show you another video very shortly, just to enable you to understand the concept.
Stereolithography is a rapid prototyping process used to create parts from 3D CAD data in a matter of hours. SLA is a highly accurate additive manufacturing process and may also be referred to as rapid prototyping or 3D printing. Models created with this technology are typically used as concept models for form and fit studies or as master patterns for molding techniques. The SLA process begins when CAD data is sliced into thin cross-sections or layers, typically about 6/1000 of an inch thick. This data is then transferred to an SLA additive manufacturing system containing a vat of UV durable photopolymer. The machine begins to build the part one layer at a time. Each layer is constructed from an ultraviolet laser that is directed by X and Y scanning mirrors. As the laser traces the cross-section on the surface of the resin, the liquid material is hardened on contact. Once the layer is complete, the build platform is indexed down to make room for the next layer. A recoater blade moves across the surface, ensuring that the thin coat of fresh liquid resin is evenly spread over the object. The laser continues to trace and form each layer atop the previous layer, building from the bottom up. The completed part is then carefully removed from the liquid and separated from the platform. A chemical bath removes excess resin, and the part is cured in an ultraviolet oven. Any support structures are removed at this time. With numerous hand sanding and professional paint options available through service providers such as Solid Concepts, stereolithography has become an excellent economic choice for rapid appearance models. A wide variety of industries have embraced SLA, including medical, automotive, entertainment, aerospace, and consumer products.
Okay, so that is another technique that was demonstrated. Basically, talking about stereolithography concept. And this concept is just as we have gone through. Now, this is a typical stereolithography machine, and that is also used in realizing that technique. Now, we want to talk about the second technique, which is the laminated object manufacturing. Now, laminated object manufacturing is basically a technique where we have layers of adhesive coated sheet material which are being bonded together to form the prototype. Now, the material may be consisting of a paper laminated or a heat activated glue, and that is rolled up. And there's a feeder or a collector mechanism that advances the sheet over a build platform, and then where the base will have to be constructed to form. The next, what happens is that the roller hits, a heated roller applies pressure to the bond and to bond the paper to the base. Now the focus laser will cut the outline of the first layer into the paper and then cross hatches the excess area, and then finally you build the part. But I'll just show you laminated object manufacturing in this concept from the video here. This is a 3D concept, a solid glue.
Solid presents its 3D desktop printer. Introducing the SD300 Pro, the world's first 3D desktop printer. With its compact size and unprecedented cost effectiveness, this breakthrough product is making 3D printing available to any office. From concept modeling to final product, save time and money with the SD300 Pro. Now go from concept to final product without using a service bureau, thus reducing costs and time to market. The SD300 Pro, revolutionizing the way designers and engineers approach 3D modeling. Plug-and-play desktop installation. With the SD300 Pro, operation is made simple using the user-friendly instruction manual provided with the material kit. Install in a matter of minutes. First, insert the engineered plastic roll into the printer. The engineered plastic roll used in the SD300 Pro is both durable and economical, giving you attractive build cost per model. Second, insert the glue cartridge. Third, insert the anti-glue cassette. Finally, place the 3 anti-glue pens. Now just hit the build button on the provided SD-View software and your printer is off. Finally, a 3D printer you can afford. The model is created by layers of engineered plastic. Following sheet lamination, the cutting knife goes to work directly from your CAD data. The engineered plastic roll is layered using special glue, resulting in strong and flexible models. The anti-glue pens then apply masking fluid for easy support removal, allowing even the smallest details to be created. Reducing development costs and time to market. Models are designed down to the smallest detail, and the engineered plastic roll is available in transparent or opaque colors. You now have your finished model in hand, ready for evaluation, without ever leaving the office. Multiple applications. The models produced by the SD300 Pro are so detailed and accurate that they are perfectly suitable for all stages of production, including rapid manufacturing. They can be machined, drilled, finished, joined together, and painted. Larger models can be created as well, assembling one model or multiple models to each other. And all of this while showing no distortion over time. Now, Solido invites you to add another dimension to your printing and change the way you design forever with the SD300 Pro.
So now it's laminated object manufacturing, another 3D printing concept that we saw. Now, the other concept is called selective laser sintering, which is also a technique that uses a laser beam to selectively fuse powdered material, such as nylon or elastomer or even metal, into a solid object. And it will build the parts on a platform which will then sit below a surface in a bin of a heat fusible powder. The laser will trace the parting, the first layer, and then sintering it together. And then the platform will be lowered to the height for the next layer of powder to be applied. And then that process continues until the part is fully built. So I will want to also show you another video, which is a fairly 7-minute video on it, as it's kind of fast.
Rapid manufacturing of any design, rapid response to any change. That's the speed and effectiveness of Northwest Rapid Manufacturing LLC.
Imagination knows no bounds. Something this intricate traditionally can only be made by hand. We can realize a design like this can be rapid manufactured in less than 24 hours.
Fast. Northwest Rapid
Okay, so this is a basic, this was a commentary, more or less. We saw from it the laser sintering. It's a documentary of Northwest Manufacturing. They specialize in this technology. They use it in producing a lot of products. So we basically saw that laser sintering technique, very versatile, and as they said, that once it can be manufactured, once it can be designed, it can be manufactured. Then we have, so that is the laser sintering. The fourth one is the fused deposition modeling, FDM technique. Simply by controlled extrusion, you have a heat depositing very thin beads of material onto a build platform from layer, the first layer, and then the platform is maintained at a lower temperature so that the thermoplastic will harden quickly, and then it lowers into, and then another extrusion head comes in, and there's another layer. So I'm going to show you that fused deposition modeling technique, fused deposition process.
You can build durable, accurate parts and models in either ABS, polycarbonate, or polyphenol sulfone by simply sending files right from your desktop or over your network. Strong and functional parts are built from your 3D CAD files using patented Stratasys fused deposition modeling technology. Powerful Insight pre-processing software imports STL files and automatically slices the parts, generating the necessary support structures and extrusion paths, maximizing build efficiency while minimizing user involvement. Inside the system's heated build envelope, model material in filament form is heated to a less viscous state for extrusion. The model is built layer by layer from the bottom up. On each layer, the extrusion tip follows a precise tool path created by the Insight software, extruding thermoplastic modeling material along with any necessary support structures. When applicable, Waterworks provides the final step, enabling complex geometries and fully functional assemblies in a single build. Soluble supports are simply dissolved in a water-based solution, resulting in a part with smooth surface finish and fine detail intact.
Okay, so that is the fused deposition modeling concept. Now the 3D inkjet printing concept was also shown by looking at the SolidView 3D desktop printer. Basically, the 3D, the parts are built upon a platform situated in a bin full of powdered material, and then the head selectively deposits the prints in the binder fluid to fuse the powder together, and the unbound powder will remain as the support to support the parts. And as the platform lowers, more powder is added and leveled, and the process is repeated. When the finished part, what we call the green part is then removed from the unbound powder. The others is blown off. So for the finished part, you can use other sealants to improve the surface finish. So for 3D printing, that we've already watched the 3D printer video. Now for solid ground curing, which is the final one, solid ground curing is somewhat similar to the SLA. Now that uses UV to selectively harden the photosensitive polymers. Now, in a nutshell, solid ground SGC, which is a solid ground curing technique, is like how the photocopier works. You have a photosensitive resin which is sprayed onto a build platform, and then the machine develops a photo mask, like a stencil of the layer, and then that photo mask is printed on a glue plate above the build platform, and using electrostatic process similar to that found in the photocopiers. The mask is then exposed to the UV, which only passes through the transparent portions of the mask to selectively harden the shape of the current layer. So after the layer is killed, the machine vacuums out the excess liquid and then sprays wax in its place to support the model during the build. So let's look at that SGS process in this very quick short video here, the SGC process. So basically you have the polymer being the powdered polymer, and then the photomask shines upon the polymer, and then you have another layer coming, and then you have the photomask shining on it, and then that process continues layer by layer until the whole part is finally built. So that's basically the rapid prototyping technique of solid ground curing, which is SGC. Okay, so that brings us to the end of this series. That's Unit 6, where we looked at rapid prototyping, rapid concurrent engineering. So basically, by way of self-assessment, you can look at the questions that are listed here. The Unit 6 assignment is shown there. So the question is, using a product of your choice, describe how the product can be manufactured by a rapid prototyping technique. So you select a product of your choice, and then you actually describe how it could be manufactured using any of these techniques, that is, any of these rapid prototyping techniques that we have looked at. Right. And then the second assignment is using a company of your choice as a case study. You discuss their evolution to concurrent engineering. That is, if you have a company or you use any company, you look at their previous manufacturing processes and then what they do currently. You research into various companies and then report on their evolution to concurrent engineering if they are actually in that practice. So that is the two assignments that is in Unit 6 that you have to look at and report on them. So thank you very much for staying up with me, and have a good day. That actually ends the lecture for the CAD/CAM course. Thank you.